Okay.
But it actually works. I know, she never gets it.
Yeah,
I need pressure.
Oh my god.
She never gets
the awkward things that when you said. The awkward things.
Did you have the recorder on?
I don't even see it here.
Guys, is anyone here in charge of the yearbook at all?
Okay.
We gotta put a section in there.
Yeah. Favorite quote.
Guys, I need to change my most embarrassing moment to kicking myself in the face outside while I was walking by.
Tell Ivy.
You look surly. You got
kicked
fat
yourself
lip. I
in the
kicked
face.
myself
Was that
in the face.
Rio?
Yeah. I was walking into. No, here. Let me explain it. So I was walking into the JO meeting and the little kicks were going on. And I was like, I can show them. So I start kicking and I kick myself with my knee and throw it like that. And I was laughing really hard and then I touched it and it was bleeding. And then I was like, and then it got really big. I couldn't play my trumpet for a week.
Oh, wait.
No, that is on record. So, but okay, Jeff. Online, I just want to point out a couple things. I did post on stats here. I did post a test online, the chapter 3 and 4 test. It's not due for a little bit, so that is online. I did post a lot of stuff here. You don't need it all right now. I did post the chapter 5 notes. I posted the chapter 6 notes for the next 2 chapters after this. If you have a hard time printing them, go ahead and I'll get them printed off. I also posted the 5 and 6 homework assignments.
When are we having the test?
And that's what I'm talking about. And I also posted the calendar, how we're going to finish this book off for the end of the year. So it has your assignments, not your assignments, but the sections we're going to cover for the rest of the year. So right now I have on the 26th, chapter 3 and 4 tested here.
So that's next Wednesday?
Next Tuesday.
Next Tuesday. Oh.
So I have chapter 3 and 4 testing here. So you got a few days here. The online's already done. Some people already done it. That's good. You got stuff to do in your book, homework problems to hand in and stuff like that. So we got that. I kind of put out chapter 4 a little bit longer because of the fact I'm going to be gone tomorrow. Tomorrow will be a work day. And then Friday I'll answer some questions. Hopefully finish up chapter 4 Friday. Monday, answer questions. And then Tuesday we'll take the test. That's kind of the plan. Was that?
Monday, snow day, Wednesday.
Yeah.
Does it smell like strawberry shortcake?
And also some of these tests, and kind of a reference, 5 and 6 we are doing together as one chapter test. And then we have a few chapter tests that we'll do separately. Chapter 7 we'll do separate, 8, 9, and 10 we'll do together. So some of the chapters we'll do together and some of them won't. So I'll tell you if you print out this calendar, you can kind of tell what chapters we're doing together, which ones we're not.
Are we starting like 5 and 6 is new stuff, isn't it?
5 and 6, this is kind of the end of the old stuff. 7 and 6 is going to be all new stuff from there on out. And also, if you look at the calendar, the reason I put the calendar out there is because, like I said, the other classes, much with help, but in here, we had to get so far through the material, and as we did snow days, we don't add them until after, right now we're adding them after you graduate. So we don't make these up, so we have to make up the time in class to get done by the 23rd. So if we miss a day here, we have to find time to make that up. That or you just do it yourself. And like pre-calc, like last year, remember some of those days you just did it yourself. And that's kind of what happened this year too. So hopefully there's not too many more snow days. I'm guessing, I'm hoping it starts thawing out pretty soon if we can go off in the middle of March. That'd be nice. So we'll see what happens. I don't know how far we'll get today. We'll talk about the rest of the probability today. I think we're about this page, I think this is where we left off. Pretty close, right?
Yeah.
Complements and the probability. We talked about probability when we did the other day, and complements we talked about the other day. And the complement, the one that's hard to do, remember that all probabilities have to add up. When you add up all the possibilities, they all have to add up to 1, right? 100%. Okay? And so when we do a problem like this, at least one. Something that's hard to do. And the reason I say that is because let's say I have 15 possibilities. If I have 15 possibilities, at least one means I have to do the probability of 1, probability of 2, probability of 3, 4, 5, and add them all up, right? One of the things they talk about here is at least 1 is the same thing as probability of 1 minus probability of none. And what I mean by that is this. 1 represents 100%. All the probabilities add up to that, right? Probability of none means that's the opposite of at least 1. So if I took that one case and subtracted from 100%, the rest of the cases would add up to that percentage. Going through it. So for example, okay, the Neckwear Association of America reported that 3% of ties sold in the United States are bow ties. Okay? If 4 customers who purchase a tie at random are randomly selected, find the probability that at least 1 purchased a bow tie. So if we're doing this at hand, you got 4 people. So there's a couple ways of doing this. We can find the probability that 1 purchased it, plus the probability that 2 purchased it, plus the probability 3 purchased it, that's 9, plus the probability that 4 purchased it. So we can do all those, figure out each one, and add them up as we go. It's going to take some time. Or what we can do is use it, since it's at least 1, what we can do is we can say this is the same answer as 1 minus the probability of none of them purchasing. Same answer. Now, if I do this, what we have is 1 minus probability of none, okay? If 3% of the ties sold in the United States are bow ties, if 4 customers are purchased a tie at random, find the probability at least 1 purchases a bow tie. What's the probability that none of them purchase a bow tie?
97%.
97%, but it has to take it times, remember independence now. 97% the first person, 97 second person, 97 the third person, and 97 the fourth person. Correct? So we're going to multiply those 4 together and work that out as we go through here. 0.97, 0.97 all the way through. And I don't know what you get when you multiply that out. You get 1 minus
0.88529.
29. Okay. And if I subtract that now, is the probability at least 1 is going to be 0.11471. So about 11.47%. When I work it out. Not a hard problem, but just kind of how different ways to do it. Sometimes it's better to go backdoor on some of these problems than try to figure out the original way. Okay, questions on that one so far? 4.4, fundamental counting principles. This is where some of the rules get to be fun. We're going to start doing some permutations and combinations and stuff. The fundamental counting rule is also called the multiplication of choices. In a sequence of n events in which the first one has k possibilities, the second one has k2 possibilities, and the third has k3, and so forth, the total number of possibilities of the sequence will be multiplying together. What does that mean? It means, for example, I don't know what with this problem. I did in high school. It says, if you go to your closet and you have 5 pairs of shoes, 10 pair of pants, and 12 shirts, how many different outfits can you pick? And what the fundamental counting principle says is you can just take 5 times 12 times 10 and you can number of outfits you pick. That's what this rule says. They're independent of each other. You just multiply them together and it tells you how many outfits. So nothing really fancy as you go through. A paint manufacturer wishes to manufacture several different paints. The categories include the following. 7 different colors, 2 different types, 3 different textures, and 2 different uses. How many different kinds of paint can be made if you can select 1 color, 1 type, 1 texture, and 1 use? So if you're going to select 1 of each, how many different types, how many different can you make? So what fundamental counting principle says, we just multiply these together. So on this one, we would have 7 times 2 times 3 times 2, 84. And which is, I don't know, 6, 2, 84. So we get 84. So we're just going to go 7 times 2 times 3 times 2. Fundamental counting, not a hard principle. Now, factorials and permutations and combinations, okay? Factorial is the product of all the positive numbers from 1 to the number. So in other words, if I asked you what 8 factorial was, what you would do is go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? And 0 factorial is always 1. Factorial means if I asked you a number combination of something happening, how many times can you choose 9 people from 9? How many ways can you arrange 9 people? You just write down 9 factorial. Now, a permutation here, and we're going to use this a lot in probability, is an arrangement of objects in a specific order. Now, order matters, and this is the thing you have to remember. Order matters in permutations. That's a key point. You use a permutation when the order matters. The formula, not very hard. It's usually written here. It's a little hard to read the letters here, but it's NPR. The number of choices, how many you're choosing, NPR. So I might have 10 choices, I'm choosing 3 choices. Like this one says 6, 3. 6 choices, I'm choosing 3. And what you're going to do is it's a factorial, n factorial over n minus r factorial. As you break it down, and solving it down for your answer. It tells you how many options there are. Order matters. For example, if I was saying I have 10 boats in a race, how many ways can they finish first, second, or third? Order matters, right? So what my problem would be set up as is I have 10 boats in a race, and I am choosing 3 boats. So I'm going to set up this problem. Solving it down would go 10 factorial over 10 minus 3 factorial, which is 7 factorial, correct? Nothing hard there. If I was solving it by hand, I'd go 10 times 9 times 8 times 7, and just like that, over 7 times 6, all the way down. These will cancel off. So really what I have is 10 times 9 times 8, which is 720. So there is 720 ways those boats can finish the race. 10 boats, how many ways can they finish first, second, or third? Now, that is a different problem than this. If there's 10 boats in a race, how many ways can 3 boats finish in the top 3? Now, does it matter if you finish first or second or third? No, it doesn't matter. It could be the ways you finish in the top 3 means if you're in the top 3, you're okay. That's not a permutation. That's going to be a combination. Formula. Permutation is when order matters. Combination, order doesn't matter. Formula for combination is a little different. Combination is n factorial over n minus r factorial times r factorial. Or the permutation divided by r factorial. This is where order doesn't matter. Suppose the business owner has a choice of 5 locations which is established their her business. She decides to rank each location according to certain criteria, such as price of the store and parking facilities. How many different ways can she rank the 5 locations? So you got 5, you're ranking 5, right? What is this one?
Permutation is the order.
Just 5.
Could be 5 factorial because you're picking 5. It'd be a permutation, but it could be 5 factorial, right? You're picking 5. I would go with the permutation because the order doesn't matter. You're ranking them, right? So this one would be 5 factorial or
Wait,
a 5 permutation 5. Either
Wait,
one will give you the same answer.
you're picking 3.
Are we
Only
picking
the top
3?
3.
They're picking 5.
Yeah, each location.
Rank only the top 3 out of the 5 locations.
Which can she rank the 5? I don't know if you're in the same problem. 442.
Oh,
So this is the permutation, right? So going there. Now this one, suppose the business owner is saying wishes to rank only the top 3 of the 5 locations. How many different ways she can rank them? Still a ranking, still a permutation, correct? But now what's going to happen here is you're going to have 5 values and you're ranking them. You're ranking 3 of them, correct? Now, you got a formula here. Another thing you'll notice is on your calculator, under, I'm gonna give you a second for my calculator start. Just to show you a couple of things where they are in the calculator. So here's our value. If you go under menu, go down to probability, you have factorial, you have permutations, you have permutations. If I was doing this one with a permutation, I would go down to permutations. It says NPR on there, and I'm going to do 5, 3. I have 5 to choose from. I'm choosing 3, right? And it should give me an answer of 60 different ways I can do this from. Noticing again, the previous problem we had 5 factorial, so only thing about 5 factorial here is I might put in the 5, and then if I was using factorial, then put that in. Hit the button. Don't hit the button first and then factorial. Put the number you want to do factorial first. And hit the answer, you get 120. So 5 factorial is 126. And then you have your combination button underneath there too. Combination is set up the exact same way, probability, combination, and if I was doing this one with a combination, you should get a lot fewer choices. Combination should give you smaller choices, smaller number of choices as you go. Okay, so you know where where those are hard to use, are those?
So how would you make this problem into a combination?
For the business owners, what do you think?
Right.
If you're going to say, instead of ranking, just say a business owner has 5 locations and they want to pick 3 of them to make the finals. It doesn't matter if you get picked first, second, or third. Then I just want to pick 3 of the locations to make the finals.
So it can't say right.
Yeah, it can't be ranked. If I said I'm just going to pick 3 locations, how many ways can I just pick 3? It doesn't matter if you're picked. You know, another example you can have in here is, if I said I got 10 people in this classroom and I'm going to pick 3 people out to get $5 bills.
So it's more random.
It's more random. But if I said, okay, I'm going to pick 3 people to get $5 bills to, it doesn't matter if you're going to be the first person, second person, or third person. You're going to get a $5 bill. That's a combination. Now, if I said, I'm going to pick 3 people out, the first person I pick gets 50, the second person I get 10, and the third person gets 5. Now, order does matter. It's going to be a permutation. A television news director wishes to use 3 news stories on an evening show. One story will be the lead story, one will be the second story, and the last will be a closing story. If the director has a total of 8 stories to choose from, how many possible ways can the program be set up? You take your choice. Write down what you think. You decide if it's a permutation or combination to see what you get for an answer. Okay, what do you think? Combination or permutation? Order matters. If you're a lead story or a second story, you better be the lead story or the second story. You have 8 stories, you're choosing 3. So this one would be a permutation. So you would go on and go 8 P3, and you get an answer of how many?
336.
336? 336. Sound good? Okay, next one. Permutation, combination. With a play, now you can pick two plays, right? You can pick two plays. There's a play, if you go, one's gonna be in the fall, one's gonna be in the spring, does it matter if you offer it in the spring or fall? If you pick two plays, one's gonna be in, is it different to offer a play in the spring and a different one in the fall than vice versa?
Kind of.
They're both gonna be played, don't they? This is a tougher one. I was thinking permutation tough. I was thinking that because I'd say, okay, if I offer, I don't know, two plays. If I offered one play in the fall and then another play in the spring, then another combination would be offering that other play in the fall and the first one in the spring. It's different, right? It would be a different combination, different order. So I would still think this one to a point. I'd probably accept either one, but this one to a point would be a permutation because the order matters in the spring or fall how they're offered. I would probably go with a permutation. You could defend a combination in this one, but it'd be a little harder to do.
Only 20 double.
Next one. So, newspaper editor has received 8 books to review. He decides that he can use 3 reviews in his newspaper. How many different ways can these 3 reviews be selected?
No, that is more than that. You can just say, oh, we can try that.
And then this one is a combination. Does it matter which 3 he picks, what order he picks them in? No, this would be a combination, this one. So you would have 8, choose 3, and you get 56 out of it?
Yep.
You get 56 different ways of doing this problem. This is a combination. A little harder. What do you think? Combination, but it's a set of 2 combinations. They're independent events, so you, what was it? You multiply them together. So the first one here, you got 7 women, and we're choosing 3 of them, so we're going to have 7 choose 3. That'll give us how many different possibilities there are for women. Times, there's 3 committing 2 men out of the 5, so we're going to have 5 choose 2. And we'll multiply those together and get our final answer. Both of our combinations, like the independent events, one does not affect men and will not affect the women, so you would multiply the 2 together. I don't know what the answer is. Here is my guy answer for me. Was it? 350?
Got 7.
You get 750?
Added
Anybody else get 350?
Yeah.
350?
permutation.
Okay. 350 different possibilities. This is kind of how we're going to work with some cards a little bit too. Okay. Probability in the counting rules. No, this is 4 or 5. I think it's one of the last sections here. The counting rules can combine with the probability rules in this chapter to solve many types of probability problems. By using the fundamental counting rule, the permutation rules, and the combination rules, you may compute the probability of outcomes of many experiments, such as getting a full house with 5 cars at dealt, or selecting a committee of 13, 3 women, 2 men, from a club consisting of 10 men, 10 women. The card thing is tough. It's very hard to, some of those are very hard problems. A store has 6 TV graphic magazines and 8 News Time magazines on the counter. And 2 customers purchased a magazine. Find the probability that one of each magazine was purchased. Okay. Now, what is probability? Well, definition. Good over possible. Okay, so probability. My pen's dying. If you think about this, probability is equal to good outcomes over total outcomes. Good over total. Correct? Okay. Let's do total first. How many magazines do we have? 14 magazines, and we're choosing 2. I don't care which 2. Total means I don't care. So I'm going to do the bottom. It doesn't matter which order I pick them. No, so the bottom is going to be 14 combinations. Because I got 14 magazines, I'm choosing 2. It could be 2 of one kind, it could be 2 of the other, or it could be 1 of each, whatever order. Okay? Now the good outcomes is this. I want to choose 1 of each magazine. Right? So how many ways of the 6 magazines here, TV Guide, graphic magazines, there's 6 magazines and I want to choose 1 of those times there's 8 of the News Time magazines and I want to choose 1 of those. Correct? You got a probability. Good outcomes over total outcomes. So what's probability happening?
48 out of 91, or 0.527.
48 out of 91 at the bottom? 48 out of 91, or actually it's like a little less than 50%, right?
A little more than.
A little more than 50%, okay. 48 out of 91. Right in a fraction of 0.5 something.
0.527.
Okay, so 0.527. So does everybody follow me on that one? These are the ones that I feel are the hardest to do. Okay, combination lock consists of 26 letters of the alphabet. If a 3-letter combination is needed, find the probability that the combination will consist of the letters A, B, and C in that order. you tell me to start? The denominator is really neither more of a counting principle. It's not the combination or permutation. It's more of a counting principle. The reason I say that on this one, I want you to look at the words. And it says the probability of the combination will consist of letters A, B, C in that order. The same letter can be used more than once. So if I was going to say 26, choose 3, can I get the same letter more than once? No. On permutation, can I get the same letter more than once? No. So I can't use a combination or a permutation if I can't get the same letter more than once.
Can't you do permutation, choose one, choose one, choose one?
You could do combination 3 times or permutation 3 times on the bottom. What I would do is just a counting principle. How many choices are there for the first letter? How many for the second letter? And the third letter is? So the denominator would be 26 times 26 times 26. That's what I would do. You could use a combination 26, choose 1 3 times. But on the total possibilities in the denominator, I would start out with 26 times 26 times 26. And Marcus, you have an answer? Nope.
17,576.
Now top. Good outcomes. Good outcomes is how many good outcomes are there? A, B, and C, right? Only one that works. So the probability that you want to get the right combination is one out of that 17,000. Actually, on top, the good outcomes is, this outcome is the only good outcome. So it's just 1 over that. That's the only good outcome. 1 over 15,776. So the probability of getting the right combination.
You get the first 5. You have the first 7 and the 5 mixed around when you said it.
But I need 1 over that number. So usually 1 works, right? Now think about that. That's a lot of different possibilities.
How much are the combination locks that we have here at school? That's like what, 45 or?
Well, think about the probability. Let's do this one. Think about the probability of winning the lottery. So,
Write down somewhere.
okay, what you're going to do is go like this. Think about how many numbers. I think there's 55 numbers, I believe, in each one. Now you're going to pick 5 numbers, right? And then you pick the Powerball. The Powerball can repeat. So let's just think about good outcomes over total outcomes. So if I had this denominator here, here's my 5 numbers. Four, 5, and I'm going to go like this. There's my power, okay? If there's 55 numbers in pi, okay? The first number, how many possibilities are there? 55. Second number? 54. You use that first number, you can't repeat them. 52 and 51. But now on the Powerball, you can repeat that number. So that's back up to 55. Now, when we go over this, how many good set of numbers are there to win the Powerball? 1. So we would take 1 over this would give you the chance of guessing the number of Powerball. So if you work this out, what number would you get? It's a big number, right? On the bottom? I don't know what little number, but it's a big number on the bottom. Your odds of winning the Powerball are very slim.
Actually, the odds that they had for, like, actually at the listing that they actually officially have is like 17 million more than 17 million for all of them.
Or something like that, but it's a little different. But no, I want to think about this. You know, when you guys go on the computer room right now, and for beginning year, and you had to set up your path on the computers, and it was certain 4 letters and 4. No, it had to be a number, a symbol, or something like that, or it had to be 8 letters long, or whatever it was, right? Why we do that is because the way people can number combinations. The more letters there are, the more numbers and combinations and symbols you use, the more possibilities there are, correct? Probability of somebody breaking your password is slimmer with the number of possibilities. Now, I always think it was funny, as you watched over the years, I mean, 3 years ago, I had a 6 or 7 letter password, and it was a great password back then. Now I have a symbols and everything password in there, and my password's 10 letters or 12 letters, and it says, need more. It's poor password, because it takes, the machines out there are so much more advanced and quicker to solve, break a password. So I remember going to a workshop that talked about this, probability of breaking a password with a computer or something like that. And he said, if you had a 10-word password, 8 to 10-word password, it would take the computer, and this is like 12 years ago, it'd take the computer probably an hour and they would have your password broken. Now, if you had like a 16 to 20-word password, he said, it'd probably take you about a day, but not much longer to get it in your computer. So when you see these TV shows where they're breaking into with passwords and breaking in on, it doesn't take long. You know? And a good example of that was last night. I didn't know this. I have a spreadsheet with a lot of formulas on it for a negotiations thing, and I haven't used it for 5 years. I forgot my password. And I know my password was 12 or 13 letters long or something like that. And didn't remember it. So I went online and I found a template for this for Microsoft Excel where you put this macro in and it will tell you the password.
I gotta find it.
So I didn't know it, so I plugged it in and did the macro in approximately 4 seconds. It tells you how fast this program was. This is a 13-word password, and they told me in like 4 seconds. So it's amazing what times it's changed, of how fast they have the password. When I downloaded it, it simply said, "We trust you. You're using it for the right reason." But it is amazing how times have changed. So when we tell you to use all these symbols and stuff, it's because it's too easy to break into. As you go through. Question on this one? Not much, right? And actually, we are done with the chapter. Now you have a bunch of work to do. I think you got homework assignments, right? Lots to work on for the next couple of days.
Yeah.
I got a feeling Friday and Monday, what I'm hoping to happen is that you guys will come with questions for me. Because I got a feeling that last section, this one on combinations and permutations, when you put them together, it's the hardest. So come with those and see what you can come up with. So see what you work on. So you have about 10 minutes today. Get going. See what you can get done. So. And like Matthew said, after we're done with this chapter, it gets all new from here.